And for every one of those iron objects that created a 5-mile crater, there were probably 10 times as many stony objects that did not leave a crater.
I was asking why they're able to predict the course of everything in the universe, but they didn't predict this planet coming to so close and suddenly
asteroid
appearing out of nowhere.
Right.
How can it be so?
Well, it's kind of like this, I guess. If if there was an elephant running by out in the street out there, you'd probably notice it. If there was a mouse running by out there, you probably wouldn't notice it. So that's a big factor right there. The size is almost everything. I mean, if you've got an object that's 5 or 6 or 10 miles in diameter, we could potentially see that, months in advance. I mean, remember Shoemaker Levy 9 was probably 5 or 6 miles in diameter before it fissioned. And we saw that thing, a year and a half before it hit Jupiter. We can see comets out there, way out there, if we know where to look. The thing is, though, that we realize is that there's a lot of stuff that we can't see. There's smaller stuff whizzing around that we just can't see. And also, a lot of work recently, like by a number of astronomers. I know Chandra Wickramasinghe, I brought this up a couple of months ago and mentioned that his work is showing that there's a whole class of objects out there with very low albedo surfaces. You know what that means? Doesn't reflect, right. So they're basically almost invisible. Now those things can be fairly large and go completely undetected. Stealth, yeah, exactly, that's right. I mean, no, that's right, yeah. And, that has caused some worry there that, that there's now this whole new potential class of objects out there that could, encounter the Earth and that would have a low level of predictability to it. The thing that buzzed us Monday, it was small, but it was like, I think, estimated to be no more than 40 meters. But that puts it, 40 meters, that's 50 feet in diameter? Tunguska-sized, yes. Yeah. So if that thing had, flown in, I mean, it could have wiped out half of Atlanta if it came in at, 40,000 miles an hour. Because remember, the punch is going to be a factor of its velocity. You double its velocity and you multiply its energy 4 times. It's an exponential relationship. So, I mean, it's just the whole idea. I think I used the analogy a couple of weeks ago here. If I had a little .38 caliber lead slug and I threw it at you, at 50 miles an hour, which is probably the hardest I could throw, it might sting a little bit, but it's not going to do any damage. But if I shot it out of a pistol and it was moving at, a couple of thousand miles an hour, that same little piece of lead would do extraordinary damage because that's the kinetic energy that it's carrying. And it's the same idea with a cosmic object. When it comes in, I mean, especially if it comes in as a head-on collision. If it comes in as a head-on, we have to add Earth's velocity of 18.5 miles per second to whatever the velocity of the object is. And it's likely to be at least that much. And if it comes at us from behind, now see, the Tunguska object came from behind, so it wasn't moving that fast. It came in the morning. It was part of the morning torrid meteor shower, and so it came from the direction of the sun. That's why that one was not seen until well, of course, 1908. I mean, there were telescopes. We could have seen it potentially if we'd known where to look, but nobody even imagined. But that thing came from the direction of the sun, and so people didn't see it until basically it was right on us. And that's why a lot of the eyewitnesses described it as looking like it was disgorged, discharged right out of the sun. They said the sun threw this thing at us. You know, that was some of what the eyewitnesses thought. You know, and when you go back and you reread some of the ancient myths about offsprings of the sun god, it makes one think possibly, you know, we could be looking at such a thing, because a number of the meteor streams, the way they're configured in space, depending on the time of year that we're crossing them, I mean, if they're throwing stuff at us, it could be coming directly from the direction of the sun. Jerry.
Hear about the other one? I saw it on the news. You know, they said it was the size of a pickup truck, and it was visible in daylight.
When was this?
I don't remember. I didn't write that down.
Right, now see, that of course isn't going to, I mean, if it fell, like for example, if it fell directly on you, Jerry, it would probably take you out, but...
When they said it was real small, but it only went through the atmosphere, didn't it?
It went through the, yeah. I mean, things the size of pickup trucks enter our atmosphere at least several times every year. At least several times every year.
They saw it today, and it was on the news.
Yeah.
That was in Texas, I believe.
Yes. A few weeks ago. Right.
Like they showed moving through the sky?
Probably.
They showed that on television.
Yeah.
CNN, yeah.
I just wondered if you had seen it.
I didn't see the video of it. I actually have on here a video of the Peekskill meteorite, and I was going to try to show it once, and I didn't have the right software, and it didn't work, but since then I've put that QuickTime on, so maybe it would work. But the Peekskill meteorite was possibly a member of the Torrid stream, and that was a pretty impressive. You could certainly find it if you went on you know, YouTube or something. I would guess it's probably posted up there. But it was a multiple fragmentation event, and several of the videos taken of it, because it flew right over like a football stadium during a football game. And one of the best videos of it, they're, you know, sitting there, you're watching the football players out on the field, and they're videoing them, and then all of a sudden you hear somebody gasping, and then the camera goes up, and then you just see this big fragmenting blaze of light going across the sky, and it was moving relatively slow too.
That's the one that, what, 17 years ago? The trunk of somebody's car?
No, I don't think that was that one. The one that, well, that was the one where it hit the person. See, that was a weird event, because like 10 years before, almost to the day, on the same block, a meteor had crashed through a lady's roof. And then like 10 years later, a meteorite comes down and crashes on her neighbor's car. So that was rather weird. We started talking a lot about the Dog Star, which, by the way, is right up here shining down on us as we speak, isn't it? Right up here, Orion the Hunter and the Dog Star, part of Canis Major. And we kind of looked at how the Dog Star was important to what ancient culture? Who? Mayans. Who else? Who regulated their whole calendar around it? Egyptians, yeah. And what was the event by which they marked the beginning of their Egyptian year? The Heliacal Rising. And what does that mean, Heliacal? Helios. What's Helios? The sun, rising with the sun, yes. And let's see if this will work. And I thought what I would do here, if it works, is pull up the Voyager movies and go to sunrise.
Now, wait a minute. That's going to be a rerun now.
No, this is not a rerun. This is not a rerun, because I tried to show this, but it didn't work, see. Okay, this is going to be, the date of this is July 4th, 2012. July 4th. Get the date? Okay, now we looked at this, but the thing was, it didn't line up quite. And I thought, you know what? We're not looking at it from the right vantage point. All we have to do is shift our vantage point to the equator. And then look what happens on July 4th. Every July 4th, well, first of all, let's take the big picture here of what we've got. Yeah, you can see the Pleiades right here. They're always easy to identify. So this is Taurus right here. So you see there's going to be Jupiter and Venus are going to be close to a conjunction. And what we're going to do now is we're going to watch, this is going to be sunrise. I'm going to have two versions of it. I think one version with the natural sky showing the sunlight, and one with the not natural sky where we see the sun rising, but we still see the stars. So when I start this thing, what you're going to see is this will be rising. And so this is what you would see on July 4th. In fact, you can see it this year, but I've done it for 2012. Let's try this again. Okay, here it comes. Okay, so you can see here the sun is coming up. It's getting light, and the actual orb has not come over the horizon, but there's the orb. Stop. There it is. Now there is the heliacal rising of Sirius. This is actually the same configuration that marked the Egyptian New Year. The heliacal rising of Sirius, when they rose together on the horizon. And you can see how perfectly the alignment is. So it's interesting to me that this becomes a very significant astrological configuration with the birth date of America. And we can actually see that this progression of this heliacal rising extends over a period of several days from the 2nd, the 3rd, and the 4th. Actually, the 3rd is probably even more accurate than the 4th. But you know, the whole convention where they were deciding the declaration and all of that actually lasted from the 2nd to the 4th. So while they were basically laying the groundwork for the birth of America, astronomically, the same event was going on that was the most auspicious astronomical event to the ancient Egyptians, around which they, oriented their entire calendar, was this event right here.
Think they knew what they were doing?
Oh, who? The founders? Well, that brings up an interesting question, whether it was a conscious thing or whether it's something, an archetypal force working through the subconscious. And I haven't made up my mind which it is. Although, given that so many of them were Freemasons, and within the Masonic tradition, Sirius plays a preeminent role, I wouldn't be surprised if at least some of them were conscious. Perhaps Benjamin Franklin, I know, was somewhat literate astronomically. So I would suggest him as being a prime candidate for somebody who may have actually known what was going on. You couldn't really see. The thing is, what's cool here is with this computer software, we can simulate what would be very difficult to see with the naked eye. So the Egyptians, of course, on this morning, you would barely see Sirius, although you could see it, because Sirius is the brightest star in the sky. However, it was in the several days leading up to the heliacal rising where basically they would go out and you could see Sirius rising, coming up somewhat just before the sun broke the horizon. So Sirius would be visible for several mornings prior to the actual heliacal rising, which is what we see here. And what we're seeing here is almost a perfect heliacal rising.
Why you choose the 2012, not this year?
I don't remember, other than the fact that perhaps 2012, the alignment is about as perfect as it gets. Because of the precessional motion, this relationship is slowly shifting. That's why we're talking about July 4th now, but to the ancient Egyptians, it wasn't July 4th.
What day was it?
Well, it was a day that corresponds to roughly our July 23rd. But of course, the calendars, Jeremy and I were talking about this on the way out here. It's so complicated that it's very difficult to explain. And that's why, one reason why I got this software, because sometimes just by seeing it, because we've got several things going on here. We've got the tropical motion, we've got the sidereal motion, and we've got the precessional motion. And making sense out of integrating all that into a coherent, that takes some mental effort. But let's look at this again. Well, let's take a look here. And this one is what you're talking about? Well, this is the same date. Well, let's watch this, because this is the one I believe where this light does not obscure. All right, so here we go. And I believe this is the not natural sky. So in other words, yeah, here comes the sun. And there's Sirius.
Green triangles all across the top of it.
Which ones, Dennis?
Was the green triangles at the top of the blue line?
Oh, that? Yeah.
They show up when the sun comes.
The numbers.
Yeah. These right here, see, this is due east. And due east is 90 degrees of azimuth, it's called. If you know the difference. There are, basically, astronomers will use 4 coordinate systems, and the one that's the most readily accessible to somebody without instrumentation is the azimuth system, latitude and azimuth, like what we're seeing here. And that basically means that if you face north, that's 0 degrees, and it's based on the horizon. And that, of course, changes with every position on the surface of the Earth. So azimuth rising of this, now see, this is at the equator. So you only see this when you come north. See, you don't see this alignment. Or when you go south of the equator, then what happens is the whole map of the sky tilts. So this is July 4th from the equator. That's what you need to remember. And we're looking due east. So you can see that the Sirius is rising to the south of east. The sun is rising to the north of east. Because this is not spring equinox, is it? If it was spring equinox, the sun would be rising right here. So this is in July 4th. So between March 21st and July 4th, the rising position of the sun has shifted from here to here. And you can see that's 60 degrees of azimuth. That's 90. So here's roughly 25 degrees of azimuth. No, 40 meters in diameter is not going to cause a mass extinction. But it would blow up with the energy of a large atomic bomb. That would blow up with an energy greater than the bomb that they dropped on Hiroshima. So it would be significant if it came into the atmosphere and exploded over a populated area. And again, you know, I will repeat what I've been saying for 10 years now. I think that we're overdue for an impact of a Tunguska scale event. And I hate to take this position, but it's begun to appear to me that in order to get people to pull their heads out of their buttholes and pay attention to the larger reality of which we are a part, it's probably going to take a mortality event of 1 million people getting wiped out. My only concern would be, well, of course I would be concerned if 1 million people got wiped out, but I would also be concerned that it could be misinterpreted as a nuclear event. And in fact, you know, there was in the mid-90s, there was in fact, I have it on one of my other programs here, but it was a declassified Pentagon report where they had been tracking atmospheric detonations similar to Tunguska, but of course much smaller. And I think the largest one they tracked was an event that might have been in the small atomic bomb range. And this was a period that that reached over a 20-year span, roughly from the mid-70s to the mid-90s, when they declassified the report. And it really does show that every year there would be 3 to 4 events where objects would come in and explode typically 10 to 15 miles up. So if they exploded with the force of a small atomic bomb 10 miles up, it's not going to do surface damage. See, we're talking about objects like the one over Texas, which you said was the size of a pickup truck. If you go up to, see, the cutoff is going to be about 40 to 50 feet. Less than 40 to 50 feet, you're going to have a hell of a light show. But it's probably not going to do surface damage unless you're standing right in the strewn field. If the stuff reaches the surface of the Earth, you could get, I mean, like something that could crash through the roof of a house, you wouldn't want to get bonked on the head by it, clearly.
Unless it was all metal, right?
unless it was all metal.
One of these chondrites, the stony ones would break up, but if it was a hunk of metal, then
See, what Brad just said is very important in understanding this phenomena. Again, as we've talked about, is that the properties of these things vary widely from being, you know, even if you like, there's one scientist by the name of something Frank who about 10 years ago was hypothesizing that every day Earth is bombarded by small icy comets. Ice that were maybe 10 to 20 to 30 feet in diameter. And of course, those don't do any damage at all to the surface. And they're mostly dissipated high in the atmosphere. But if you run the whole gamut, if you can think, picture this would be a good way to illustrate it. Like you come in and I've got a snowball, I've got a typical rock, like you pick up, you know, on the side of a road or on the side of a creek, and then you got a piece of cast iron. And that whole range, that pretty much runs the gamut of densities of the things that potentially strike the Earth. On the low end, you've got roughly the density of water. A low density comet is like a snowball. In the middle, you've got a stony asteroid or a carbonaceous chondritic meteorite, which is going to be, you know, 2 to 3 grams per cubic centimeter. The standard is water, which is 1 gram per cubic centimeter. So a low density comet's going to be almost like getting bombarded by a snowball. Well, yeah, except the thing is if the snowball is moving at 30,000 miles an hour when it hits, you know, that could be some significant effects. And then at the other end of the spectrum, you have the iron meteorites, which are extremely dense and heavy, you know, 5 and 6 grams per cubic centimeter. So when you get these light objects, they come into the atmosphere and they'll fragment and never reach the ground. And if you're out in the daytime, it can be a major detonation event 10 miles up and you necessarily won't even see it. If it's at night, you'll get a flash of light that can actually, you know, cause trees to have shadows and everything. The middle of the road is like the Tunguska object. The Tunguska object was, they asked, most of the American scientists believe that the Tunguska object was probably a stony asteroid. So fairly lightweight, not like a piece of cast iron, but it was because of that reason that it was not able to penetrate fully into the atmosphere. Now, if it had been double or triple its volume, yes, then it probably would have penetrated all the way the atmosphere and reached the ground. Now, if we look at the meteor crater in Arizona, the size estimate of that object is about the same size as the Tunguska object, about 50 meters in diameter. But there, and we know this from the actual fragments that we found, it was an iron asteroid. And so there's a really good cosmic lesson to learn. A middle density object like a stony asteroid, 50 meters in diameter, does not reach the ground. The same sized object that is an iron meteorite does reach the ground, blasts a hole into the ground just like you detonated an underground nuclear weapon. So that's the difference. Now, there's another very critical fact that has not been appreciated, I don't think, by too many people, even astronomers, and that's this. The iron objects are much more likely to hit the ground than the stony objects, right? Also, when you look at the distribution of size, the census of size, the smaller objects are way more abundant than the larger objects. You know, just like mice are more abundant than elephants, right? The larger the object, the less of them there are out there. That's why some scientists, particularly of the British school of catastrophism, their main concern is not like a big Everest-sized mountain slamming into the Earth like that took out the dinosaurs. Their main concern is a swarm, for example, of smaller stuff the size of Tunguska. And maybe another metaphor to use would be like the difference between, if you think of getting shot with a .45, it's going to leave a big hole in you, you know. But you get shot by a 12 gauge shotgun, you know, it's going to leave a different kind of a wound. The thing that took out the dinosaurs was probably like a .45. It was a big planet buster that came in, created a crater 10 miles deep and 150 miles wide down in the Yucatan. But if you have a swarm And, you know, this might be what we're looking at with the Carolina Bays. The Carolina Bays may be the fingerprints left by a cosmic swarm, where you've got like just this shitload of cosmic buckshot coming in, encountering the Earth. And that is a very real scenario. But the thing is, when we look at the census, the distribution of the different kinds of objects that are out there, what we discover is that the stony asteroids are 10 times more abundant than the iron asteroids. Now, what does that mean? It means this, that if you look at all craters that are left on the Earth that are, say, less than 5 to 10 miles in diameter, they were probably all created by iron objects. And for every one of those iron objects that created a 5-mile crater, there were probably 10 times as many stony objects that did not leave a crater. So when you see discussions amongst astronomers and whoever about the probabilities of, you know, there being an impact, if that is based exclusively on crater counts, it's going to be very misleading, because crater counts alone are going to bias it extremely towards the low end. Because for every crater under 5 miles in diameter, that was probably produced by an iron object. But the much more abundant stony objects are not leaving those craters behind. They're blowing up in the atmosphere, just like Tunguska did. You would probably continue to blow up in the atmosphere until you got 300 or 400 or 500 feet in diameter. Once you hit about 500 feet in diameter, the stony objects are probably now going to be impacting the surface of the Earth. So what that means is that that I've always interpreted is that, you know, the biggest threat to us is probably a Tunguska-sized object, but not coming in alone, because, you know, our studies of the Taurid meteor shower would suggest that there are clusters of Taurid-sized objects. And then, of course, when you begin to read the literature from, you know, the ancient times, a lot of their descriptions sound very much like a description of a multiple impact event. Well, yes. And let me pull out something here. Now, this is, to me, extremely interesting, because it leads to this whole cosmic architecture that I think is going to be necessary for us to really comprehend in order to see how these cycles are unfolding, where we are in the cycles, what happens at the critical junctures or the nodal points within those cycles. This is a book that I've referenced a number of times in here called Hamlet's Mill. And you know what the premise of Hamlet's Mill? Hamlet's Mill was this book published in 1969, I believe. It was the life's work of two scholars, Hersha von Deschend and Georges de Santayana, I think is what, wasn't that the two authors, right? They concluded in this big 500-page tome, 600-page tome, the whole premise of the book was essentially that the ancient world, the archaic world, had known about precessional motion, the precession of the equinoxes, long before supposedly it was discovered by Hipparchus. Was it Hipparchus or Aristarchus? Hipparchus, yeah. Before it was discovered by Hipparchus, what, 500 BC? 300 BC? 100 BC, okay. Give or take a few centuries. The whole point is that it had been understood in the archaic world, perhaps even thousands of years before Hipparchus, who is now credited with discovering it, okay? Anyways, it's a book, it's a hard book to get around, but it's definitely worth reading. I mean, what they do as far as bringing forward the idea that there's a scientific basis to the archaic mythology is probably, you know, they should be credited along with people like Joseph Campbell and so forth, who helped to bring the idea of mythology and place it on a firm scholarly basis, and evolved beyond this idea that it was just a bunch of superstitious gibberish that ignorant pre-literate, pre-scientific people came up with. Anyways, this is what they're talking about, the Tammuz.